All right, so we're all recording. Please click on recording. All right, so the meeting is being recorded. Let's just check that to see if it's on, it's going. All right. Normally when it's on recording, I am not seeing. I see a little, okay, I'm seeing it, yeah. It is recording. All right, so let's go ahead now. Okay. So today we'll be looking at, we'll not look at everything on this profile. We'll try and go down to at least velocity time graph. That's where we want to head to. So we're going to look at Newton's law, analyze the motion of a body for kinematics. All right. We're going to also look at the kinematics linear motion equation, and we're going to look at the kinematics equation for angular motion. And likewise, we want to look at the velocity time graph, right, for velocity time displacement graphs and so forth, right? We will do projectiles another day, right? So I hope to reach as far. The slide is about 150, so it means that we'll break it up probably in 3 parts. At the end of this slide should finish the course. Technically, we should finish once we finish this slide, right? This body of information is quite a bit, right? And it will finish the course. So when we release it to you, everything you see there, these are the final slides. Unless I add anything, I may add something individually to the slides. All right, so let's look at what we have in front of us. All right, so the first concept.
Sir, is this slide available in Moodle?
It should be available. I may have not released it.
Sir, I always have something. Yeah,
Sir, you're saying it should be available, but you say it's not been released. That means it's not available.
I'm just checking to see if.
Sir, can you send it in the WhatsApp group?
No, hang on. We just check it if it is released. Hang on a second, please. Let me just make sure that everybody is seeing it in Moodle.
No vibes.
Because I can't send it in the WhatsApp group. Hold on, let me just pause recording a little bit. I'm pausing the recording and I'm going. Yes, so we now be looking at Newton's law of motion, as we have here. And Newton's law of motion, you have Newton's first law, which states, as you can see here, about an object at rest will remain at rest unless acted on by some unbalanced force, right? Some unbalanced external force. And an object in motion continues in motion, right? With the same speed, in the same direction, unless acted upon by some unbalanced external force. So in my days, we normally say this one in a little bit different way, talking about if it will continue in some line of action, if a straight line, unless it is interrupted, it will continue to move in the same direction, right? And it's pretty much the same thing. So we are saying here, if the object is moving, continue to move in the same speed, in the same direction, unless some external force or something stop it, it will just continue to move in its direction. So that's the first law is saying, and it starts to do quite a bit with balance and equilibrium, right? So if it's in a state of equilibrium, it will continue to be, and if it is not, it will continue to be in a state of equilibrium, unless some external force acted on it in either way, typically. And the second one now, one that you must throughout your engineering life, is going to be very fundamental to a lot of laws and fundamentals, is one that we have to talk about force, mass, and we talk about acceleration. So acceleration is produced when a force acts on somebody with some mass, right? The greater the mass, the greater the amount of force is needed, right? For the body to accelerate, right? So this law, this one, is when we talk about F is equal to MA, right? And you'll be seeing that in quite a bit of the equations, right? And right throughout. The second one, everybody know that one. So if there is an reaction or some action in one direction, we're saying that there's an equal action in the opposite direction. So typically, for every action, there's an equal reaction. Some person may say it that way, right? And we use this one even outside of physics. We are saying we use this in our lifestyle to say, if somebody do bad, somebody else may do bad or do good, and there's good. So what, for every action, there's an equal reaction. So that's we use that in our life. So you can just use the parallel to it. But in physics, this means, and in statics, it means different things in terms of motions of body, right? Right? You could think of momentum, right? And they'll talk about momentum before, you can momentum after, and so forth. So we'll get to those laws, right? Right, so these are the fundamental principle on which everything else is built. And once you understand these laws, then you are good to go. So let's continue. So what causes motion, right? So we talk about motion in a lot of situation in terms of statics and dynamics. So we have pretty much most of the topics that you have done before, the bodies never really move. Huh? They're in static. So we are not in static anymore. We are more in what we call dynamics. So dynamic now is where the body is moving, the body is accelerating, the body have a velocity, it have some displacement, right? In respect to time, right? So we involve time, rate of change of displacement and all of that in this aspect of it. So all change in motion are caused by the action of some forces, right? And force cause acceleration, and that acceleration is equal to the change in velocity, right? So mechanics, right? So mechanics is a branch of physics that seek to explain motion and the force that cause the change, right? Cause the motion to change. So one, we look at kinematics, right? And we look at dynamics. We previously looked at static bodies, bodies that don't move, bodies that don't necessarily accelerate. There's no acceleration for anything that we did before. That was a static, and we tell you that the bodies don't deform. But the difference now, we're going into what we call kinematics, is a branch of mechanics which describes the motion of bodies or object. System of body without considering the masses of these objects, nor the force that may be cause the motion. Right? So this is kinematics. And now we are moving into dynamics, which is a branch of mechanics concerning the study of force, torque, and their effect on motion, as opposed to kinematics, which studies the motion of object without reference to its mass. Newton defined the fundamental physics of law governing dynamics, especially the second law, which I mentioned before, which talks about a body, a force, body as a result of a force, right, and its mass, and the acceleration that it will have. So F is equal to ma is the second law of Newton. And that's where the fundamental principle, a lot of this material is based on in dynamics. All right, so we'll be looking further now. Here, we're focusing the branch of kinematics for this lecture, and requires quantity that we'll be looking at. We're looking at time, and we know that the standard unit for time is S, right? And Displacement is in meters. Velocity is meters per second. And acceleration is meters per second square. So remember now, we would have looked at dimension analysis. And we know normally for time, we put a big T. But in terms of the unit now, is S is represented. And for displacement, we normally put a big L, right? But its unit is meter. And for velocity, which is meters per second, we normally put L upon T for dimension analysis. Or we put L T to the minus 1 for the velocity. And likewise, the acceleration would be L, which for the meters, and T to the minus 2, or L divided by T square, right? So those are normally how we do it for dimensional analysis. But the standard units are in meters or seconds. And these are all used interacting with these equations, right? Now, the first thing we look at is what is called displacement, right? So normally we talk about distance and all that, but we want to look at displacement is a vector, right? So there's a vector that points from an object's initial position to its final position, right? So somebody can move a distance, but they must move a distance arbitrarily. The difference is for displacement is a distance in a particular direction, right? So the initial position of its final position. So the objects have an initial position and it has a final position in a specific direction, right? Over a specific time. And so we call this displacement, right? So it's a distance in a particular direction. And its SI unit, of course, is meters. So for example, if the car starts at a particular point and it finishes, it starts at some point, initial point I, it will finish at some point F, which means XF, which is the final place where the vehicle will stop. And so for the displacement, we can say it's the difference between the final position and the initial position, and it is denoted here as delta X. Right? And that's different from distance. So sometimes we talk about distance, do not mix up distance and displacement. Displacement is in a particular direction. It has an initial point of start and a final point. And it has direction. All right. Likewise, velocity now is defined as the rate and change, or as you could see here, the displacement per unit time. Whatever is convenient for you, whatever you remember it, fine with me. So if I ask you what is the displacement, then you put displacement divided by time, not distance, then that is correct. And so displacement, as we said before, it has an initial point that you start, and it has a final point that you reach. And that also will be time. It have over a particular time. So you'll have an initial time and it have a final time. Once you are able to compute that, then you understand what is happening here. So if you can see this little drawing here, it says time taken by the car, right? Pardon me. So I don't know who. So here now, I can't take any calls now. Right. So let's see it. Let's see. Is there anybody in the waiting room? Everybody, I think it's automatic. Everybody is in. Okay, fine. All right. So okay, so we are saying here, time taken by a car in displacing from A to B is 30 seconds. And the distance cover, some initial point is moving between some displacement here. So he has an initial starting point and a final starting point. So he may start at A and end at B. And that total displacement is 600 meters. And the time taken is 30 seconds. So it means, therefore, your velocity is going to be the 600. The 30 divided 600. And that will give you 20 meters per second. Right? So you move from initial point A to some some final point B, and it is also time, right? And you divide it. So it's a ratio of the displacement to the time, and it gives you the velocity, which is meters per second, in terms of your unit. All right. Let's continue. Okay. Now, what about acceleration, right? What about acceleration? I trust everybody is still hearing me. Okay, so the acceleration is a rate and change of velocity now. So everything is interlocked in here now. They're intertwining. So acceleration is a rate and change of velocity. First, we look at displacement, right? And now we say that the velocity, we see that velocity was equals to what? Displacement divided by time. Now we're looking at acceleration, which is what now? The velocity divided by time give us acceleration. So it's a rate and change of velocity with respect to time give us acceleration. And it is a measure, and it is measured from how quickly the velocity changes. And the SI unit, of course, as we said before, is meters per second square. So you start at some initial point, and we normally donate it by what? V1. Or some people use U, mean initial velocity. So in different hex and different material, it is donated differently. So in this slide here, you're seeing that it has V1, but in some text you will see it has a U, right? Which means it's the initial velocity, right? And then some of them just write V, final velocity. All right. And this one, T, initial time, final time. All right. So here now we can see that we have the change of the velocity, the initial velocity minus the final velocity divided by the time taken, the total time taken. The total time is the initial time minus the final time, and that gives you the delta. So you get from that, you will get the delta V, and you will get the delta T from as a result of that. All right. So it's quite simple there. Any question, you can stop me and ask. All right. And I'm hoping that some persons were exposed a little bit to it before, so that will be easy. So we'll just refresh you. For a body object traveling linearly at constant acceleration, we can write down a few simple equations that tells us the relationship between one that we mentioned before, displacement, velocity, and acceleration. And all of those are kind and called kinematics equations, right? The equation will include the following parameters. So S is equals to displacement, U is the initial velocity, V. So just before I told you that sometimes we use U for initial velocity, V for final velocity, and A for acceleration. All of these now, we're going to look on a set of equations that we use to work out different problems based on the rules that we are applying. Okay, so we consider an object that has initial velocity U and a displacement, right? Right, at some point. So let's say the displacement is 0 and the time because it's we're gonna start, it is 0, right? The body moves at a constant acceleration a for a time where t is in second, all right? And so from this, we can formulate an expression which says your acceleration is equals to your final velocity, right? And sometimes I write v, and this of course is u for your velocity. So your final velocity, this fancy v represent final velocity. Get used to it because you'll see more of it, right? Get very familiar with it. You see more of it, right? So you can say that the final velocity minus initial velocity upon t. And so from this, if you cross multiply, right? If you cross multiply a times t, you get at. 1 times all of this, you'll get v minus u. And so our first equation of motion is equals to v, your velocity, equals to u plus your acceleration times time, right? So it's a product of your acceleration and your time, right? So the body will have an initial velocity time, and then it will have a final velocity. So your equation 1 relates to velocity to the time, right? And this is known as your first equation of motion, right? Where your it gives you initial velocity, it gives you final velocity, pardon me, initial velocity, and it gives you the having acceleration times time for that one. All right, let's continue. All right, equation, another equation that is important to us is equation 2 and equation 3, right? So there are equation here where we talk about average displacement, right? You remember we talk about that displacement is velocity was what? Displacement upon time. So therefore from that we can say the average displacement is equals to the average velocity time time. When you hear the word average, it means that there is something divided by 2. So if you're averaging a set of numbers, you would have divided by 2, eh? If you have 10 numbers and you're adding there, you want to find the average, then you would have to divide that by 2. It's similarly, we have an initial velocity and a final velocity, right? So if you notice, average velocity here is having a little v and a little dash over it to say that that's the average. So it's average of it. So it's v with a little dash, represent average right there in the formula times t. So that gives you an S is written for displacement. So S is a symbol. In the past, we used to use X for displacement, but now we're more using S for displacement. It has changed over time, things has evolved. So average velocity is initial velocity, because you must be summing 2 items. So it's initial velocity plus your final velocity upon 2 that you have right here, right? You see it's right here. And so you have initial plus final velocity divided by 2. That gives you your average velocity times time. And from this, we can also interlock the first equation. Remember that this was the first equation of motion. All right, so this is the first equation of motion. If you were to substitute now the first equation of motion from this displacement formula, average displacement formula, you can now get that the average displacement, and you substitute wherever in this formula you're seeing. Let me clean this up a little bit. Clean this up. All right. So wherever in the formula, all right, in the formula you're seeing that you have V here, which is final velocity. But now you know that final velocity from your first equation of motion was V is equal to U plus AT. So right in this formula here, right? Displacement formula, you're gonna put in that here, put it in right inside here. That was where you have V, right? And that now gives you a new expression where you have U, and they have another U here plus AT. So you get 2U plus AT here. So if you look over here, right? Now you have 2U plus AT, right, times T. And you all you need to do now is to simplify this expression. You multiply 2 by T, right? If you multiply 2 the numerator, you'll get 2UT plus AT squared upon 2. But all right, now you know that this can further be simplified by dividing each of the quantities up top by 2. So when you divide, so see it here now, this now equals to 2U T upon 2, right? And right, so you break up in this form, and this simplify, the 2 years cancel, and here now you get UT plus half AT squared. And this is now your third equation of motion. So this is giving you displacement is equals to the initial velocity, the product of initial velocity times the time given, plus half AT squared. So if you really wanted to know how this equation was formulated, where it came from, this is how it was arrived at, right? This is how we arrive at this expression. Any questions so far? All right, so let's run along. Therefore, hang on a second here. What am I having here? What should I do with this thing? I don't want it up here blocking my. All right, thank you. So there is a variation to how equation 3 is stated. So equation 3 can be stated, right, that U plus AT, you can also say that no, that is displacement, right? So we can have a further equation. So it's U plus AT, right, plus half AT squared, right? Now, your delta S, meaning that some final distance to some initial distance was what you started with, and it ended up giving you this expression. So your final displacement, remember you had an initial one, so it is equal to UT plus half AT squared. This is now quantity is now your initial displacement, right? So since the objects tend to start from an initial 0 position, which is SI, equation 3 is usually stated as the displacement equals to UT plus half AT squared. But be sure to properly analyze the details of the motion. So you must be careful because you must start from some initial point and to reach some final displacement, right? And then now we're gonna look at another equation of motion that we can use when we have certain quantities. So it's very convenient for another one. And this one now, what's the relationships we have here? So the equation of that we have, 4 of them relate to displacement and velocity. The first one was V is equals to the initial velocity plus the acceleration, the product of acceleration and the time, right? So from this one, if you were to square the quantities on both sides, you will get that the velocity square is equals to U plus AT square. This now, you are going to get a quadratic expression, right? Once you square it, once you square one side of the equation, anything you do to one side, you must do to the other. You will get V square is equals to U plus AT. So you're going to get U plus AT times U plus AT. Now, all you do to do here is U times u, give you a u square, and then u times 80 gonna give you 80 u80, right? And then if you multiply, you take this one now. So first thing you do this, then you do that, and then you go another writer, and you multiply again, and you go with that one because it's a quadratic expression. So first one we get u plus 80, right, for 1, and then you have u plus 80. You start with this one again, you're gonna get another u plus 80, and then the final one you get a square t square, and that now gives you v, your final velocity square is equal to initial velocity square equal to 2 u80 plus at square, right? Now that can be further be simplified. If you look at the last section here, we can factor out a 2a out of this. So you take out a 2a out of this, you get ut, and you divide it, the 2a in this, you're gonna get half at squared. Does this look familiar that you know what this was before? Didn't you have an expression, didn't we have an expression a while ago that looks similar to that? Equation 3, right? Isn't this looking similar to it? So right there now, you can see that this now, all of this is equals to S. So you can see u plus half at squared is equal to S. And we drop it in and we get our fourth equation, right? That the velocity square is equals to the initial velocity square plus 2 times the acceleration times the displacement, right? And therefore you have your fourth equation of motion, right? So if you don't have time, but you have the initial velocity, you have the acceleration, then what depends on the quantity that you need, you can use this formula, which is quite straightforward. Right. So there goes, we have equation 1, right? We have this one for average displacement when you just have the velocity and the time. And then we have equation 3, and then we have equation 4. So from that, we have our 4 kinematics equation that everything else is built on, right? And there is, when we look at angular motion, we're gonna see the parallel between these equations and others that we'll formulate. All right, so let's look at a problem. So the initial a vehicle, initially a car traveling along some straight road, having some speed, right? And the speed here is 35 meters per second. So that's the speed, the initial speed that it have. And speed here is the same thing as your initial velocity. So if the brakes are applied now, after you have started, and the speed of the car is reduced, now it's reduced, you know, not increased, it's reduced to 10 meters per second. So that becomes your final velocity in 15 seconds. So it means that between your start and where you stop, it's 15 seconds it takes you to do that. You must determine your constant deceleration of the vehicle. Deceleration means that you are decreasing because you are not once you are not accelerating, you're decelerating. So your deceleration, right, of the car means that you're slowing down. Here now you have your initial velocity, which is u, is 35 meters per second, and the final velocity is 10 meters per second. Now we can apply our first equation of motion, which says that final velocity is equal to initial velocity plus your acceleration times the time, the product of the acceleration. So here now you simply do a substitution. First thing you need to do Wait, so when you see a problem, you're going to list out what is it that you have and you don't have, and what they ask you for. So you go and you write U equals, see there, 35 meters per second. You put V is 10 meters, so you can list them out just like we have it there. And you put the T is 15 seconds. And then now they say to you, you must determine your acceleration. So you know that that is what you need, question sign. And from that, you know that everything that you look at it, the first equation of motion will help you, because you see that there is a velocity, final velocity, initial velocity, acceleration time, and you don't have this quantity, right? So you can say, I'm going to transpose. So transposing from that, you would simply say, okay, acceleration, I want it by itself because I know that V minus U is equals to AT. And so when you have two quantities, once you take this over from one side of the equation, it is minus. Then you know you have a product. Acceleration time is a product. To separate a product, you must divide. What is it that I want to make the subject of the formula? Isn't it the acceleration? So you're going to have to divide 2 by T, both sides of the expression. And therefore, you have V on U on T equals to AT divided by T. And so as such, you can say now that T cancel T, and you end up with final velocity minus initial velocity upon T, right? And so you get your acceleration. So from that, we simply make a substitution. You could put it in the formula immediately, and from there, you work it out. But I'm just showing you, for just reminding some persons how to use the formula. So V minus U upon T. So here you have your final velocity is 10 versus the initial velocity, all up on your time, which is what, 15 seconds. All right, and when you finish, you put in your units. Please put your unit in. So you'll have minus 25, right, all up on 15, because the vehicle is decelerating. All right, so that's what the minus sign represents. And you see the answer there, 1.67. All right, and you notice I put the arrow here to represent that the vehicle is decelerating. It is not increasing, it is decelerating. All right, so let's go again, move on. So another example, let's look at another one. So a car starts from rest, and with constant acceleration, achieve a velocity. So it starts from rest, some initial point, then it achieve a final velocity of 15 meters per second. And when it's traveling with a distance of 200 meters. So its displacement is 200 meters. That is a specific direction. You know, you see the word distance there, its displacement is 200 meters. Right? So here now we see our final equation of motion that we did. Is quite useful for us. So what is it that we need? We must determine our acceleration. So you go again and you say V square minus U square, right? Because you're gonna take the U over, will give you 2AS. And you want what now? A, so you're going to divide 2 by S, both sides. Anything you do to one side, and you're going to divide 2 by 2A, which is what you need to get. So you want to make A the subject, but you have 2A multiplying it. So the 2AS, so you must take 2AS, divide both sides. And that will cancel that, that will cancel that. And therefore your acceleration is V squared minus U squared upon S. So that's just giving some persons a reminder, how is it that you do transposition, or you transpose for a formula, right? Once you see that you have U squared on one side, you don't need it, you take it over the other side, it's a plus or minus, but then now you end up with 2AS, but the 2 and the S are the quantities that you want to separate from a product. So only way you separate a product is by division. All right, remember that's a a product, which is 2a, which is a constant, time a variable, two variable, a times s. So you have to take out the 2s and separate it. So from that, you simply put in this now and you will get your acceleration. But when you finish here, you only get acceleration. You want time also. So from that now, you know that, okay, fine, I don't get the time from this initial, this fourth equation of motion because there's no time in it. You have to also use the first one now. Now that you have gotten velocity, you have final velocity, initial velocity, and you have the acceleration. You left that you still have an unknown, and you know that t is going to be equal to v minus u upon a, right? And so your final velocity was 15, your initial is 0, divided by your acceleration that you got, 5.625. And of course, you need to put in your unit because your time is there, and you get your answer, which is 2.67, right? So that's simply how that is done, right? But what, so firstly, you have to recognize what is it that I want. So you list what you have and what you don't have. So you could list them simply, just like we have them up here in red. So u0, meters per second, right? V is equals to 15 meters per second, and S, displacement, is equals to 200 meter. You need acceleration, question, and you need time. So those are the two things. From the fourth equation, you recognize that it will give you quite a bit. You have initial velocity, so you have final velocity, initial velocity, you have displacement, you don't have the acceleration. So you say that is a good equation to use, right? So you can do that. After you've done that, then you move to the first equation of motion, v is equal to u plus at, because all the quantities except time is given there, and you just substitute for that. So that's pretty straightforward, all right? So you can understand it there. All right. Any questions so far? All right. I'm happy that you all understand this. Yes, somebody chuckled. Is that you? Do you have a question?
No, sir.
All right.
Oh,
Great. Fantastic. All right. Let's move on to question 3. Let's look at it quickly. It says a car is traveling at 15 meters per second. So that means it has a velocity at 15 meters per second when the traffic light is 50 meters ahead, right? Turns yellow. So you know that once you're coming up to the light and you see yellow, it says that it's a caution light, which tells you that it's red next and you need to stop, right? I know a lot of persons run these lights, but it is actually giving you time to know that by the time you reach a light, it will change, depending on your distance, or your distance from the pole, right, from that section. So it's you're to determine the required constant deceleration, because from that point now you will start pressing your brake so as to break up. That when you reach the stop light, you could have stopped. So you stop accelerating now, you're decelerating, right? So you have a negative acceleration there. And the time needed to stop the car at the light. So again, you know that your initial velocity, because the velocity that you're moving with is considered the initial 15 meters per second. When you stop, you would have come to a stop point, which that becomes the final meters per second. And then your displacement up to that point is 50 meters. You look at this now, what is it that you want? You want acceleration. So from there again, you see that your fourth equation of motion is helpful in one, getting you the acceleration, And the first one will give you your time. So you go again and you simply input your value because you know that V square is equal to U square plus 2AX. You transpose again for your acceleration. So you know your acceleration is going to be V square minus U square up on 2S, right? Because you have the displacement and you simply transpose and put it in and you will get this value here, which a minus sign, say that you're decelerating, right? And then now you similarly want time from the second equation. So you know that T is going to be equals to V minus your initial velocity divided by your acceleration. And that now you have your acceleration from up here and you notice it's minus, so you put it in, right? So here you will get, you'll put in your final velocity was 0. Initial velocity was 15, right? Upon minus 2.25. So right there you'll get a positive 6.67 seconds for your time, right? And that's simply how you do it. So one you have to do is recognize what you have and what you don't have. You look at your quantities. When you see you have initial velocity, final velocity, a displacement, right? You say, okay, I know that we have 3 equations of motion. And your initial one is very easy to remember, eh? So you know your initial one is V is equals to U, right? So you know V is equal to U plus AT, right? That one is easy to remember. Then you know you have your other equations of motion. So you could have second one or third, right, is really 4. So there are 3 of them that stands out. So V is equal to U square plus 2AS, right? And then you have your displacement is UT plus half AT square. But when you look at these, right, you typically would know that for this one, firstly, you have no time, but this will give you acceleration. After you get acceleration, you can go to this one. If you go to this one, what will be the differentiation? You don't have time and you don't have acceleration. There's too many unknown in this one here. So if you had done a substitution in this one, right, you would have a little bit of challenge because you have velocities, right? So you have to look and see, what is it that I have? And so from there, you can make your best choice in terms of what to use, right? And you know that your velocity is your displacement, right? Your velocity, you have your other velocity formulas that you could use, but these are typical the ones, and you could use the other one with the average velocity. All right. All right, so let's move on from here. Let's go on again. All right, another problem. Any questions so far? We're all good? Yes, we're all good? All right, I take that to mean. All right, so example 4. As a train accelerates uniformly, it passes successive kilometer marks, right? While traveling at velocity of 2 meters per second, right? And then 10 meters. So the train have some uniformly, it passes some successive kilometer mark. So first one it passes at 2 meters per second, then the next one is 10 meters per second. You have to determine the train velocity when it passes the next kilometer mark and the time it takes to travel the second, time it takes to travel 2 kilometer distance. Now, this is a little bit different from all the other problems that we have been working, quite straightforward. So the first thing you have to think of, the kilometer of the journey. The journey now, we know our SI unit is meters, but this is in kilometers, right? So you see that your initial velocity is 2 meters per second, and the final velocity is 10 meters per second. The distance now, 2 kilometers, right, means that you will have to do some conversion there, right? It says it's traveling 2 kilometer distance, right? So determine the velocity as it passes the next kilometer mark and the time to travel the 2 kilometer distance. All right, so we say that the distance here is equals to 1,000. So it's each mark that it passed is a 1,000 kilometer mark, right? That's what you have to recognize. So it's a successive kilometer mark. So it says successive, so it means that between 2 meters per second and 10 meters per second, that mark, the distance between those two marks is 1,000 meter or 1 kilometer, all right? So that's what it means right there. The fact that you have your velocity and you have your distance, right? Because remember it says successive, so there's a initial point where the velocity is just 2 meters per second, that is 0. When it reach up to 10 meters per second, that's another kilometer, right? So that you will do the conversion. How much meter makes a kilometer? Talk to me.
1,000. 1,000.
Right. And they tell you that it's 2 successive one. All right. Why is my right hand writing? Yes. Yes. So say 1 kilometer. All right. So that's what it means right there. So if it's 2 of them, it would mean that for every 2 gap, it will enter a total distance of 200 meters. But between the initial one and the final distance is only covering 1,000 for that point. So there now you can apply that your initial velocity and your final velocity, this equation here, which we call our equation 4, is adequate to get our acceleration from this one. So that's what we know, because we have initial, final velocity, and we have our distance between the two. So it says it's past the successive kilometer mark. Someone saying something? Could you please mute, please? I'm hearing you. You're gonna have to close that mic behind you. All right, so from that you can transpose, right, again, and you get your acceleration, which is 0.048 meters per second, right? And therefore you have your acceleration, right? But now it also wants the time. So let's run on. All right. Now let's do the next part of it. So now that you have calculated your acceleration for the second kilometer, right? Remember you had covered is 2 successive ones. So it says the train accelerate uniformly, it passes the successive kilometer mark while traveling at the 2 meters per second and then the 10 meters. You have to determine the train's velocity when it passes the next kilometer mark and the time to travel the 2 kilometer distance. So this is the second kilometer now. So now you know the initial velocity, right? You have the distance. This is the second successive kilometer mark. You would have already calculated your acceleration, right, which is 0.048 meters per second, right? So from this, you put it back in the same equation. You put your initial velocity, 10, and then you put in your acceleration, and the next successive time is another 1,000 meter, and you drop that in your expression, And from that, you work out, this will give you 100. You multiply this here, right? And you get a value. Whatever you get, you're gonna take the root of it. Everybody understand how to do that? Who don't understand how to work out something like this? So the second part of the expression, let me just work it out and show you, just for clarity and just to be clear, not taking anything for granted. So remember now, this is we'll give you 100. The second part is going to be 0.048 times 2. Give me what? 0.096 times 1,000. And it gives me, let me write, come on, writer, where are you? Where is it? It's all over the place. Need to get so this is 96. All right. Now, in order to get V, you're gonna have to take the root of that. All right. Anything you do to one side, you do it to the other. So you know the root, and the root can be worked out in many ways. So you had V square is equals to 196. So in order to get the value of that, the opposite of the square is the root. It means that you take the root, this is what you're actually doing. The root is a half, so it means that 2 times a half give you V, and the 1/5 to that index is really the same thing as the root sign. So all who don't remember, right? So that now you just take the root of 196 and then you get your 14. So you get your 14 and that is meters per second, right? So that is how it do. Once you have any index up to a half, right? What happened here in just reminding you of indices. Oh, hold on, let me get a writer here that I can see. This one is eluding me. So remember, this is V square. Just remind some persons. This is a half out here. So it's 2 times a half. So it's 2 times a half. Give you 1. So that's how we get the V here. So and that is the 1 to the 1. You don't have to write. The root is the same thing as the bracket to the half. Right? So remember those. Right? And that's what work out. So I'm just reminding you a little bit of your indices right there. Make persons catch up their indices. All right. So I will not erase it for clarity there. All right. So we move on. All right. Then it says now for the whole journey, right? Because we still need to consider the whole journey. We want the time to cover the whole journey, right? So we remember the initial velocity was that. We got the final velocity as 14. We have the acceleration. So now you can go back to your first equation of motion to get the final time, because you will have the final time, you have initial time of acceleration. So the total distance now, you substitute them back and you transpose. So T is equals to V minus U upon A. Right? What's going on here? Could you mute, please? Who is talking? Please close your mic if you have to converse. Please remember, I'm hearing you. You're disturbing us. Whose mic is open there? All right.
Oh, that's my mic, sir, but I was the one saying on.
Yeah, please close your mic as soon as you're finished, please. All right. Once you talk to me, just close it back so that if there's somebody interacting with you, they don't disturb us. All right. Have I stopped sharing? You have interrupted me now. All right. Okay. All right. So from that, you would transpose back for T, which is V minus U divided by your acceleration. And that now will give you the total time between the 2 successive kilometers. So over the 200 meter, you have now calculated the time. So over the 2 successive meters. So it says successive kilometers. It means that it covers for every kilometer, represent 1,000 meters. So it therefore means that for over both of them, the total time taken is 250 seconds, right? 250 seconds, you can divide that. Now we can work out how much time that is in a minute. You can do the conversion if you so desire, but your SI unit is in second. If you divide that by 60, then you can see how much minute that is equivalent. You can work it out. So 1 minute equal to 60 seconds, so you can do the conversion, right? But remember, we want it in SI units, so you have to make it remain in that. But in terms of, you can do conversion. All right, so that is that. And now we're going to move to another aspect of this material. So another aspect of this material that you may not be so familiar with, unlike high school, right? You have to pay attention now because some of you may have not been exposed to this before. So, as I told you, that there's a parallel between kinematics and angular motion. So first we dealt with linear motion, motion on a straight line, so to speak. Now we're going to talk about motion that has to do with angle, moving at angular path, right? So we're going to talk about angular displacement, theta, meaning that you're moving around some angle, right? You're not moving in a linear format again. You're going to consider a disc that rotates from A to B, right? So remember, we used to have CD, and the CD will spin when it's playing, right? Or you could consider that you're on a bicycle and you're riding around a stadium track, and when you reach around a particular point, we could even talk about some centripetal forces, but we're not going to take it to that level today. We're just going to say that you're making an arc, you're going around a path, and you're mapping out an angle as you do so. And that angle that you're doing, you're creating a displacement. You're moving some distance that we consider a displacement, because you start at some initial point A and you finish at some other point B, but you're not moving straight, you're moving at an angle. So as of such, you would have curved out some angle, and you know, typically a circle goes up to 360 degrees, but we're not going to that yet. We consider that you're moving to some part out of the circle, right? Some arc. So you have a circle. If you don't write around a circle, you have a circumference, but you can map out a little part. Once you take a segment out of a circle, you can have a length of a arc out of that circle, right? And so we have displacement. So you consider this that rotates from A to B. The angular displacement, right? If you look in the angle between the two radiuses, you see it maps out a point. Where's my marker? Oh, so it's you see you move from initial A and you curve a point right around here to B, right? And as such, you have covered an angle, and we call that an angular displacement, right? For you to, it's an angular displacement theta covered can be measured in revolution, right? So how many rev, right? And it's revolution, we think about degree. And furthermore, we come into another phenomenon that we talked about in terms of angle. So if we're not talking about degrees, right, where you normally put a little degree, what if 35 degree, we can also talk about something that we say, we use another type of measurement, which is radians, right? So for some angular motion, where there's a parallel angle that we use, right? We use radians. So you can either have your units in degrees or you have your unit in radians, right? Okay, how do we come up with it and what are the standards? So it was discovered that and established that 1 revolution is equals to 360 degrees. So for you to go around the entire circle, which is 360 degrees, we consider that 1 revolution. Now, the equivalent of 1 revolution in radians, it is known as 2 pi. Now, everybody remember that a pi has to do with a circle, don't? And a pi, 1 pi, it means that it's going around a circle or the circumference of a circle where we establish and get the pi. That's where pi is initiated from, right? And you can do your research. How did they come up with pi? Pi is 3.142, right? And it has to do pretty much with research that was done, and they established that the radius going around the circumference at a point 3.142 of every circle, and they established pi from that. And pi value, everybody know it. You can see it on the top of it, is equal to 3.142, right? Established. So now it is recognized that for 1 revolution, which is equivalent to 360 degrees, the parallel in terms of radiant is 2 pi radiant. So now you're not measuring in degree anymore. You're measuring here. For angular motion, we don't use degree, we use radians. So that's all we have established. So you could say now that 1 revolution, which is donated as 1 rev, is equals to 2 pi. All right? That is the angle that is used. So when you have a revolution, we can say that's equivalent, the angle equivalent is 2 pi, right? And the 2 pi is donated as radians, that is units for that establishment. So the best measurement for rotation of rigid body is the radian, right? Or some people call it rods, right? So we use the rods. 1 revolution is equals to 2 pi rod, right? People call it different thing, just to remember it, all right? So that's the establishment. So you can map out the angle here. We can say, we can establish and say what this theta here is equivalent to for this segment in rods, right? So the established thing is 1 rev is equals to 2 pi, right? Or we call it 2 pi radians or 2 pi rods, right? Typically they call it 2 pi radians, right? All right, so from this definition of radiant, it's a radiant is the angle theta subtended at the center of the circle by an arc of length equals to the radius of the circle, right? So that's the definition. So S here is equal to arc length, right? So it is the angle subtended at the center of the circle by an arc length S equal to the radius R of the circle, right? That's what it's equal to. So look in the circle and see a number of things written here, right? So they symbolize it to say that the distance cover, the arc distance, divided by the radius is equivalent to the angle here. So they say since for a full circle, S, that's the length around it, the arc length around a full circle is 2 pi r, then 2 pi r radians is equal to 360, and 1 radian is equals to 180 divided by pi, right? Pi, right? So 180 divided by pi degrees. So it's equals to, so 1 radian is really equal to 57.3 degrees. That's what we're really saying here in essence, right? So if the full circle is, let's write up here, if 2 pi is equals to 360, then half pi, 1 pi is equals to 1. Come on, writer. equal to 180. That's what we are saying there. So that's 360 degrees. All right, well, this is radiant. So one pi radiant, come on, is equals to, oh, that thing just gone. I don't know where it disappeared to. Thing clean it off. I don't know what's happening there. So I write it back again. So we're saying 2 pi is equals to 360. So there, so 1 pi is equals to 180 degrees. All right. So one pi radiant. All right. This is rods. This is rods. This is degree. All right. And if you work that out, you would saying that, so from this we can say that if you were to divide pi by, if you divide pi by pi here, and right, you're gonna get 1 is equals to 53.3 1 rods. So it's 1 radiant is equals to 57, sorry, 0.3. Right. So this is the advantage of the formula, where I can say from this here that the angle theta is equals to S upon R. So that means your displacement or the length of the arc, if you cross multiply, is going to be theta times R. Right? So that's what this formula gives you. Right? So it gives you your displacement. Right? So it gives a direct correlation between the distance S and the angular displacement. Right? Theta, as long as the angle is in radiant. Right. So we remember we talk about the length of an arc, right? And we had we know what the length of an arc is already, and this is the parallel to it, but this is in S theta, that the angle is mapped out right there for that segment. All right. All right, so let's move on because this is useful, right? So here we go now, looking at an example, but this time, the example that we're gonna look at is in angular motion, right? So we have a rope, and you wrap the rope many times right around here, right? But in order to do that, you would have tied the rope somewhere in the center here, and you're able to wrap the rope. This was somewhere down here, somewhere down at the base here, and you start to roll it up. You tie the rope onto this, and you're pulling it upwards, right? And you're wrapping it, you're pulling it, and you're winding up. So this is going up. So until you move it from the ground to some point up here, right? You have moved and rolled it up to 20 meters, right? It says 8 equals to 20 meters here, right? It says the rope is wrapped many times around the drum of radius. So the radius for this drum is 50 centimeter, which is the same thing as what? If you divide by 100, you get it in meter. So it's 0.5 meter. So that's the radius. Let's say now, how many revolutions of the drum are required to raise a bucket to an height of 20 up to this point to cover that distance, right? What do we know? We know that the angle theta is equals to S, right? Your displacement divided by your radius, right? So we know that wherever you start from, you start from some point here, A, and you reach to some point up here, B. And so you are able to lift it up using that same so when the rope is here and you start to pull it up, suppose it was up here or here, wherever it is, and then you make it reach around here. Right? Let's say that it was some point here, right? Initially on the ground or somewhere down here, right? And you are able to move and roll it up till it reach its final point to where it is resting now. All right? Here to reach its final point. All right? So you start on some point here and you reach here, right? Argument saved as an example. So you'll have covered that distance. But you're doing a rolling. What it says is wrap many times rolling up. Right? So it means that you would have done it a number of times going around. All right. So it's not like you start as a little heart, but you have been wrapping it around in order to lift it from the ground. Probably you make 3, 4, 5 revolutions. It says, how many revolutions did you make in wrapping it totally around? Right? Because you want to know, so you need to know the distance covered in terms of your revolution, right? And at the same time, you would have accomplished a virtual height there. So the angle theta is going to be the total distance, your total revolution distance around the circle represented by S. And here's the equivalent linear one down here is what? 20, right? And what is the radius now? Right? Your equivalent radius for this is 50. 50 now convert to meters is you divide by 100. So you'll get 0.50, which now gives you your angle. That's the total angle you make around here is 40 rods. So the angle that you're getting that you have made right around the circle, right, is 40 rods or 40 radians, sorry. Right? So now we need to convert it to get how many revolution, how many times did we wrap it around the drum. So you have to go back to what you know, to standard. We established that in that 1 revolution, right? Which is equals to, that means 1 time around the drum was 360 degrees in degrees. But now we're working with radiant. So we know that the equivalent is 2 pi. 2 pi radians or 2 pi rad. So, we have calculated that is 40. So therefore, how many revolution? What you have here is you just need to go back to, you know, from standard. So you go back to what is standard and what you know. And you work from what you know till you get to the unknown. So the answer is down there. Just listen to me carefully before you look at it and confuse. So you go to what you know. You know that 1 revolution, meantime 1 time around the drum, right? When the rope is rolled 1 time around it, it would have represent 2 pi. All right. But now you have 40. Right? So you need to do a little bit of ratio and proportion. Right? So if 1 rev give me 2 pi, how many is 40 rods to that? So you do a little bit of maths here. You say 1 revolution equals to 2 pi. Therefore, 40 is equals to x. And then you cross multiply. Everybody remember about them little, this is ratio. So you cross multiply, and I get a different column on right. Let's see it. So you get a, so here you would get, you would do that, do a cross multiplication. So you say 1 revolution, so you're gonna cross multiply, and you will get 1 rev times 40 is equals to x times 2 pi. All right? And you need to get x. So you're going to divide by 2 pi. Anything you do to one, you do to the other. All right? All right. And it's pretty much the same thing. This is in rods. All right. Remember that was in rods. This is rods. And here you go. This was rods too. So here, rods cancel rods. That cancel that. And only thing you're left with 1 revolution upon the 40. So you're left with 1 rev times 40 upon 2 pi. All right. And from that, that will be equals to x. So 2 into that go 1 and into that 20. So it's 20 divided by 3.42, right? And you left with rev. So x is going to be equals to 20 times 20 divided by pi, right? Times 1 rev. Come on, right? Huh? What is it thing here? So what about what is going on here? Schema stop sharing. What is happening here? Some error here. Come again, let's go. Are you seeing me? All right, yeah. So here you have it. So it's 20 times the rev, right? And if you notice, when you divide 2 pi by 40, then you end up with the answer. So that you end up to be given to 6.37 rev. So you can use a ratio and proportion, or you could use the standard that we have down here and saying that 40 rods, you know that there's 1 rev divided by, so you take the reciprocal of this, the other approach that I taught you. So you take the reciprocal, 1 rev, you know that 1 rev upon 2 pi, and it have rods down here, but you need to cancel rods. So you know, say, if it was the other way around, you would have put 2 pi upon rods. The answer here is in rods. That is what you want to cancel out and get rev. So you must take the reciprocal of it. All right, take the reciprocal and put 1 upon 2 pi and multiply it by pi, then rods cancel rods. All right, and you leave with 1 rev. This now is going to be 40 upon 2 pi. So that's the next parallel, and that answer is in rev. And that is the answer which is given you, 6.3. So any which way you want to take it, right? You could use a ratio and proportion method, or you could use the initial one that the slide teaches you to do it from day one. All right? So you could use that method. It says not. All right. So you can use that method. That is a standard method. So you just take the reciprocal, 1 rev upon 2 rod time multiplied. So the rod cancel the rod, right? Once you go across, it will cancel. All right. Any question? But is that clear? So the rods would cancel. You just take the reciprocal of this. Any question there, guys? Talk to me. I don't want to be moving. And anybody have any question?
No, sir.
No question. No question here. That is clear? Clear for everybody? Any question? Okay. All right, let's move on. All right. Let's go. Where are we again? So now let's move on. All right. So it says here now, let's continue. This is now same example. This is same example 6. So the different one says a bicycle tire has a radius of 25 centimeter. All right. And if the wheel makes 400 rev, so this time is rev, how far will the bike have traveled? So you go back to your standard, and you know that what? 1 rev is equals to 2 pi. All right. And your answer, you get a value in 400 rev. All right. So this time around, rather than putting 1 rev upon it, you have to do the reversal of it. So this time you're going to put 2 pi rods upon 1 rev, and then you multiply the 400 times rev times that. So that would cancel out the rev, and you'll just leave with 2 pi rod times the 400. So it will give you that amount of rods. All right? But then now you have to think of your formula that your displacement is equals to the angular radiation times the radius, right? So you have this, right, which is 2,113 rods, and then you multiply it by the radius, but you need to convert the radius to meter. So that is divided by 100, so you get 0.25, right? So that's angular displacement, where is equals to, so you're not using pi radians anymore, you're using the angle theta. So when we have worked it out, right, and you multiply it, so it's theta times r, that's the length of the arc around there, angle is in radiant, and you multiply by the distance, and you will get it in meters. All right. Any question there? Is that clear?
Yes,
Any
sir.
question? Very clear, right? All right,
Yes,
so
sir,
let's
it's clear.
move on. Yeah, man. All right, cool. All right. So here we go again. And we're gonna step it up a little bit more now. And we are now going to kinematics of angular motion. We've previously dealt with kinematics of linear motion, and the fact that we have established about our radiance and all of that, we can take it a little step further. We had linear velocity, which was what? V is equals to U plus AT squared for your first equation of motion. And the second one is V squared plus U squared plus 2AS, right? Your displacement. And also we had that your displacement is equals to initial velocity times t plus half t squared. Right, so you would have had some formula like that, and there's a fourth one which has to do with your average velocity, your displacement due to your average velocity times time, right? Which your displacement was u plus v upon 2 times t. That would have been the average displacement. So let's move it a little bit further. Now there's something called angular velocity, not linear velocity, and it is symbolized by a symbol that we call omega, right? So angular velocity is what we call omega, and there's a parallel between it and the linear velocity. But this is a representation of velocity in a circular or angular motion form. And this is the rate of change in angular displacement, not linear displacement now, but angular displacement. The unit for angular velocity are radians per second, right? So omega is equals to the change in the angular displacement, right, divided by the change in time. So omega is equal to theta upon time, which is same thing as rods per second, right? So your displacement here is the theta. Your angular displacement is theta divided by the time for your omega, right? And then now we have we can move it a little bit further now. So let's look at another little problem here, similar to the one that we dealt before. So we have a rope, same rope, wrap around many times around a drum of radius 20 centimeter. And we already know we're gonna convert that to meters, right? By dividing by 100. They say, what is the angular velocity of the drum if it lifts the bucket from rest to 10 meters in 5 seconds? So this time around is not 30, it raised up to 20. It raised up to 10. and it do it in 5 seconds. Now, the angle move is equal to the displacement divided by the radius. Your displacement, as we established already, to raise it from the ground, right? And its radius is 0.2, right? Because you divided the 20 centimeter by 100, and you'll get 50 rods. So it means that it makes 50 rod angle up on the jump, right? The fact that you have the angular gradient, which is the angular displacement, it means that omega, your angular velocity, is equals to the rate and change of the angular displacement per unit time. So it simply means omega is theta, which is the angular displacement, divided by t, which is 50 rods divided by the total time taken to raise it up, which is 5. And so you'll get 10 rods per second. So remember now, for angular displacement, it is not meters it measured in, it is measured in rods. And the time is still, t is in second. So your angular velocity here is rods per second. All right. And likewise, just like how you get angular velocity, we can have angular acceleration that we'll be looking at shortly. Right? And you can suspect its unit. That unit is rods per second square. All right, so let's look at this one now. So the angular motion can give us angular acceleration as it. And it is donated by alpha. So the angular acceleration alpha is a rate and change in the angular velocity, right? Which is a parallel to the linear one. The unit for alpha are rods per second square, right? Are radians per second square. So alpha is a change in the angular velocity divided by the change in time. So alpha is equal, just similar. Remember when we had linear velocity, it was final velocity minus initial velocity, and it was final time minus initial time. Well, it's similarly for angular motion, your velocity, angular velocity, your change in angular velocity is omega f minus omega I, which is equal to delta omega, divided by the change in time. Final time minus initial time give you delta t. So your alpha, which is your angular, your acceleration, is equals to omega upon t, which is rods per second, right? So you have your initial velocity, and you have your final velocities. You can look at this circle around here. You have initial versus final, right? So let's go again. Okay. So we have a problem here looking at angular acceleration, right? This is example 8. It says a block is lifted from rest until the angular velocity of the drum is 16 rods per second after a time of 4 seconds, right? So now what is it that you are given? They said the block is lifted from rest. So it was initially at rest until the angular velocity is 16. So the initial omega is 0. The final one is 16, right? And the time taken is 4 seconds. So all you have to do is to say that your difference between the initial velocity and the final velocity is 16, because 0 from 16 is 16. And your time taken is 4. So that gives you your acceleration is now equals to rods per second square, right? Similar to linear motion, but this is angular motion, which is a rate of change of your angular velocity divided by your time. Right? The change in angular velocity divided by your time. So here we have the parallel. For the linear one, it was V is equal to U plus AT, while for the angular one is omega F equals to omega I plus alpha T, which alpha is similar to the acceleration, but only the acceleration is an angular acceleration. The velocity here is final. The velocity here is final in angular. The initial velocity in angular is similar to the initial velocity in linear. And you can see them, the formulas are pretty much similar, right? This is the displacement, angular displacement. This is linear displacement. This is angular displacement, which is average of the velocity. Initial velocity plus final velocity, while this one is in initial plus final upon 2. So they are parallel to the 4 equations of motion. You have these are linear compared to angular, right? And that's something that you need to know and appreciate. Any questions so far? Everybody is clear? Are we all clear, guys? All right. Seems like we are all clear. Let's run along. So here we say a jet engine starting from rest, right? Still angular motion is accelerated at a rate of 5 rods per second. 5 rods per second is what? The acceleration, right? After 15 seconds, time taken, what is the angular velocity of the engine? What is the total angular displacement over time? So here we see that we're going to have to apply a number of equations. So the initial angular velocity is 0, which is rods per second. The acceleration is given 5 rods per second square, and the time cover is t. So we are seeing that the first equation of angular motion is sufficient to give us what? The final velocity, because the initial velocity is 0. We have acceleration and we have time. So the final velocity, omega F, is 75 rods per second. And you just do this quickly, the substitution with that, straightforward. And likewise, we need to finish up now because we said that we want now the displacement. They say, what is the total angular displacement? We didn't find that. But we know that one, we have acceleration, we had time, and what did we find before? We just found the final velocity. So we are saying here the total angular displacement is equals to the initial velocity time plus half alpha plus t squared, right? The initial velocity, if you choose to use that formula, right, is 0 times 15. So that part is gonna drop out. So your first part of your expression, right, that part will go, right, that drops out, and you're only left with half times 5, right, which is the acceleration here, which is rods per second square. And then now you have to square your time. So that gives you 565 rods, right? And I should think that the other formula, this other formula here would give you the same thing. Where is it here? This other one here, here I have it. This other formula here, where is it? See it right here? because you had you calculated the final. This initial was 0, right? You had the acceleration and you had the you needed to find that. So if you use that equation would bear the same fruit as they use in the final one. However, the final one had time, which was a good thing, you could use that. But the fact that you had calculated you had your acceleration, then you could simply use that. You could simply use this one too. All right, this one would be just as useful. All right, because you'll have used the time before. Right, so it's your choice. All right, where's it again? Your choice. You could simply use that one. What will you say that one was again? Let's see if we rewrite that one. So that was omega f square equals omega I, come on, writer, plus 2 times alpha times theta. All right, that was the formula, right? Right, so that one, right. So if we transpose for this one, we should get the same thing. We needed theta from that. So theta would be equals to omega square f minus omega I square upon 2 alpha. All right, and we had W was what was the final velocity again? It was we had worked it out just before. What was it again? 75. So that one should give you the same. 75 square minus 0 square upon 2 times 5. All right, and you should get the same thing with that approach. Just double check it. Once the formula is written right, you should pretty much get the same thing for the application of it. All right, so you get the same thing from that one because 75 square is equals to where is it? Equals to 5625 divided by 10. All right, and so you will get there 562.5 rods. All right, so you could use that formula also. And this is similar, so it's easy to remember. Same as the linear one would have been what? The linear one would have been v squared is equal to u squared plus 2as. But the difference is a is alpha in this one. Distant here is theta. So you just simply, it's the same thing. So this formula could have been used too, right? Right, either that one or the same one that we have here. Theta is equal to omega t plus half. So you could use that one also. So it's your choice. Yeah, let's move on. All right. So here we have example 10. All right, so I know a lot of you would have ride on a merry-go-round and is traveling initially with an angular velocity of 5 rods per second. So right there now, you have a velocity in rods per second. So that's your omega. All right? So it says the initial one. Come on, writer, where are you? So you're saying your omega I is equals to 5 rods per second. So that's your initial velocity. A child pushes the merry-go-round around 10 revolutions. So you see how much revolution. So you push it of all 10 revolution around. So you have the distance moved here now is 10 rev. Right? Causing the merry-go-round to accelerate at a constant rate of, so the acceleration, which is alpha, our case, is 1 rods per second square. They say, what is the final angular, which is omega f, of the merry-go-round? What do you know? So first thing you have to do is convert the 10 rev to rods. You go back to basic, and you see I have it here, that 1 rev is equal to 2 pi. So everybody need to remember that 1 rev in right is equals to 2 pi radiant. All right? So therefore now you say that if that's the case, how much rods do I have? So you put 10 rods is equal to how much in radians? Cross multiply and you will get, show you, give you another color. So here you'll get a cross multiply. So X times 1 rev is equals to 2 rods times 10 rev. You divide 2 by 1 rev, or you do it the other way that we have done it before. All right, divide by 1 rev. That cancel that. This cancel that. All right, and then you will get that your theta, or I should just put theta, I should call this theta. Your theta is equals to, depends on how you want to work it. It's 2 pi rods times 10. All right, and you would have converted the theta right there to equals to 2 pi r times 20. So this would give you in all 20 pi rods. All right, so it's your choice. You want to convert to rev, so you're gonna do what? You're gonna go to 2 pi rods divided by 1 rev, and then you multiply it by the 10 rev. All right, this is how the text, how we have been teaching you to do it. This is one way. You cancel that. So 10 times that. So that's another way to do it. All right. So that's pretty much another way to do it. And then you would get that. This is it. So they're showing you ratio and proportion here. And I'm just kind of break it across to you. You can just multiply across diagonal, and then you transpose for your theta, and you get it. Or you do it this way. All right. Whichever one easier for you. Because remember, this is the unknown. Right here, so it's the unknown. So you cross multiply. So it's theta that times this, and then that times that. All right, and you end up with this. All right, or as I said before, you put the reciprocal over. You know that it is rev here, which you need to cancel. So you must put 2 pi rods above, and you put the one that you need to cancel down here. That means when you multiply 10 rods, the rods will go, and you only will left with 10 times 2 pi rods. All right, and that's an easy way to see it. If you can't do the long cross multiplication, ratio and proportion. All right, so that's another way to look at it. Then now, after so now you have your distance, and now you set your equation of motion is omega square, final omega minus initial square plus 2 alpha t. What do you have? You have acceleration, you have your initial one, but you don't have the final. And you just simply substitute, because now you have had your distance. The rev, the 10 rev is converted to radians, see there, and you have your acceleration, and you have your initial velocity. So that's now your final velocity in rods per second. All right, and that is how you would do that. Any question? Everybody straight on everything here? Nobody have any problem in conversion? Hello? We are only down to still 38 persons. This is almost less than half of the class. I know we are recording, so the others can go through it. Right? All right, let's continue. No question. Oh, slide is so clear. Wonderful. I hope that reflects on the exam. I don't want a person not to understand and don't see anything in it. All right, so let's continue on. it says here now, example 11, a car start from rest, accelerate for 5 seconds until the wheel, what time do we have here now? A little bit after 5, I'll continue a little bit. So a car start from rest, accelerate for 5 seconds until its wheels are moving with an angular velocity of 1,000 rods per second. So that's the angular velocity. Eh? So it starts from rest and it accelerates for 5 seconds. That's the time. Until the wheels are moving with an angular velocity of 10 rods per second. What is the angular acceleration of the vehicle? So the initial velocity is 0, we're seeing there. The final one is 1,000. The time taken is 5. They are saying to you, what is your acceleration, angular acceleration? So the very first equation can help you with that, where you have final angular velocity equals to initial one plus alpha t. And you just simply substitute, because you substitute in that expression for the unknown, and you end up to have alpha is equals to 200 rods per second. Right? Right, which is pretty straightforward. So it starts from rest. Once you say start from rest, you assume that the initial angular velocity is 0 until it reaches some velocity, which is the final velocity, over the time. And so from that, you can quickly pick up that there is an initial and a final velocity. And the time cover is 5 seconds. Right? And therefore you transpose. So that would have been the best one to use. Right? Because the others, you couldn't use the distant ones because they didn't give any distant, right? So that would not have been advantageous for you to use a distant one, all right? You could probably now work out the distant covered, all right, as a result of having the acceleration, initial and final velocity. You could probably use the third equation. All right, I think it's the third one, we call that one. Where's my writer? So you could use the third one, which was omega square f equals omega.
Excuse me, sir.
Yes.
Sir, are you keeping track of the time?
Yes, I am.
So I am sure you are aware that the time has ended far long time ago.
Let me see what time is it. 10 o'clock, 10 minutes past, man.
No, sir, your class done 4:50, not 5 o'clock.
Oh my. You have another class, sir?
No, but I have things to do at home here.
At home. Okay. All right. Guess what?
Sir, you can continue now.
Yeah, we are
Continue.
recording. We are recording now. We're not gonna be much longer. We're recording, so you can review anything you would have spoken about. But I'm aware, sir. Thank you. All right. Yeah, I'm mindful. Mindful that you have other things to get done. All right. So yeah, that's that. I'm gonna stop there because obviously I will still have to repeat some of this because I more than half of my class is not here. We'll be posting the video in the WhatsApp group still. So I'm not gonna really continue much further. Let me just see how many things I have left here. We can discard that. Let me see. We are up to, so we after this, so we know that we stop at this slide here. Let me see where we are. Okay, so in next class, I will start the velocity time graph. We'll keep that until the others are here. right? So, and I will, it means therefore, I probably will have to have a makeup class because quite a number of persons are here and they probably just want to some clarity. And the velocity time graph is very important, right? And then after that, we will run into projectile motions. And after we finish projectile motion, then we will pretty much finish some aspect of this course. So we have projectiles. We have quite a bit. It'll take us probably the next 3 or so classes to finish this. Then we go into a little bit of momentum. Right?
Sir, a quick question.
Yes.
For the bridge, is it supposed to have a belly or something or not?
No. Bridge not supposed to have a belly. Somebody asked me what is needed in the assignment. Remember, I told you, once you design the bridge and you have the element, I want you to calculate some of the forces. Remember that we give you a load. The load, once the vehicle driving on it, that load, I think it was what, 480? Something like that. That load at the truck on it, and the truck
Yes,
would be
sir.
running on the deck. You are able now, you could put it at the center of your structure, which we call midspan, and you can use that now to calculate it. I'd like to, let me just take 5 minutes to talk about the bridge. So I'm gonna stop the recording here. I'm gonna talk about, well, I probably should let it stay for clarity. Let's go somewhere where we talk about the bridge a little bit. So you would have designed your bridge, right? Can you see where I'm at now? Are you seeing that I'm on another page?
No, sir. No,
You're not
sir.
seeing where I'm at? No? Hold on.
No, sir.
I have switched it, let me stop. I'm gonna reshare. All right, so I've stopped the slide and I'm now on here. All right. So I'm at this point. So I'm saying to you, for the bridge, let me just discuss the bridge a little bit. And I'll keep the recording because I want persons who are not here. Why is that my file is not? Oh, come on. Let's come out of this. Right. So let's get a tool. On the join tool here. Arrows. Yeah. So let's say you have drawn up your bridge. All right, and I've just sketched a little bridge quickly. So your bridge, say this is your bridge. All right. And your bridge looking something like that. Whatever type of bridge you choose to design. All right. Let's get a different one. This is so small. And you have elements on your bridge. Whatever choice you have them. Let's suppose that's your bridge. Right. Right. Let's argument say that this is your bridge. Right. Whatever design you have on your bridge. And then your bridge have some, so at this center, the truck driving over it, and let's assume that the center of the bridge is about somewhere here. All right. All right. So the bridge has a center there. You have a support here. All right. So you have a support. All right. You'll have a support of your bridge here. Your bridge has a pin joint here. It has a roller here. All right. So typically, once it have a pin joint here, we'll just consider that it has one support here. Oh, wow. How do I erase this thing? I want to erase this thing. All right. So let's suppose it has Come again. So suppose the bridge has a support. Right there. And the bridge has a support here. Right. Right. Now you would have, I'm expecting the calculation. Let's suppose this was A. I'm not leaving all of them. Just say that this is A, this is B. And call for whatever this is D or something. You know this load is 480 kilonewtons. I don't remember the value it was. This is now AY. This is now BY. All right. I'm expecting for you to use method of joint and go. Let's suppose this was AB. Let's say this was CD. Right. E, F, G, H, I, J, K, or something like that. And whatever. And you go joint by joint. So I'm expecting you to firstly calculate. So you must calculate reactions AY, which is easy. A and BY. All right. Those firstly. And then you're going to proceed. You have 5 of you. You're going to proceed to calculate for each member. And let me see if I can give you a color. Let me touch them. So whatever your bridge is, each member, I want to know this the thing in there. I don't need more than that. It's 5 of you. Each person take a section. And you calculate the force in the members. See there? And that's simply your bridge. All right, so you design it first, right? And this is the part now I want you to use method of joint. You could use method of section too, but method of section is only going to give you 3 at a time. You could use method of section too. Method of section, you would have to be cutting the bridge. Let's suppose here cut across 3 elements. You could cut across that. You could cut across that. But you'll have to take in them segment by segment. Right? I don't want necessarily that. That is not necessarily what I want. Well, you could use that too. And I wouldn't stop you. You can use anything you want to use. Right? You could use anyone you want to use. It is all up to you. And I don't have anything to do. It's your choice. But I would probably just use method of joint right across. But you can use method of section. So I leave it open to you. That's all I want. Just to demonstrate your understanding. So you're going to say consider. You're going to consider a joint, or you consider A. That is after you have, let's say that this now, you do it at midspan. So this is about, so AB, let's say AB hypothetically would have been 240. And this one is 240. Argument's sake. Kilonewtons. Right? When you're done your calculation and show me how you do your moments, because you have your little worksheet, you get those values. You consider joint A, and you come to, you say, consider joint A, and you say, okay, one element is that way. All right, I'm trying to look at this one. And then another one, you know, so you can draw all the forces at the joints. Let me use a tool. Look a little bit decent. So you go, another one goes into the joint. Another one goes into the joint. This one is a little bit off. Let's do that one over. All right, so you get another one that way. All right. Now remember that this one is gonna have this one would have 2 elements. It will have 2 components here, 2 components there. Remember now, you would have known what? You would know these angles inside here. Right? Based on your thing, you would know these angles. You would know your angles there. Whatever you want to call that, whatever you want to call that data. Because you would have, in the drawing, you would know these distant. Suppose that is 2. when you join, you would have known these distance. So it is easy, not like you're not working with distance. You join have all the distance, and you'll be joined between a grid, so you know the distance and you're joined. Tell me if I'm asking you too much to do. You think that is difficult? That's not difficult. You have joins there with the same dimension. It will now demonstrate that you have an understanding. So let's say that this was hypothetical. Let's say that was 30. All right. I could now say that, okay, this is 250, 240. All right. I don't know this one. This is A. And this was what? No. Everything was labeled up here. So this is AC. This is now A what now? K. This is K. So I could formulate using my equilibrium equations. For each one of them, I would use, where's my writer? I don't like when the writer is too small, I can't find it. So my writer here, so your equilibrium equation, sum of forces in X equal to 0, sum of the forces in the Y equal to 0. You'd use it for each one, all right? So you say, let's say you're doing the Y first. This is also 30 degrees for that on there. So this component would have been, this force here would have been F AC. This one would have been F AK. All right, this one is AY. So here now, if I'm doing some of the forces in the Y equal to 0, then I would say that write this equation. For this one, this is sine, so it is FAC sine 30. And for the horizontal one, the next one will be FAC cos 30. But both of them here have two components. For FAC, FAC has two components, right? So for this one now, I would, how many vertical forces I have in this thing? I have, trying to find a different color. I have two, one here going up, and I have this one going up also. So I could say now that FAC sine 30 plus AY equal to 0. And from that, I know AY already. So I need to find FAC, which is going to be equal to minus AY divided by sine 30. So therefore, that would be minus 240 upon 0.5, which is sine 5. So that's, you're going to say, and that is minus 480 kilonewtons. Argument's sake, I'm just giving you an example. And you do the same thing for the X. So you get the sum of forces in the X equal to 0. So you take joint by joint. So that's you have a little thing to do. If you can't do all, I want to do at least half of the members there. Do as much as possible, right? And demonstrate your understanding of method of joint. And you can use method of section too. You have 5 of you. So after joint on the bridge and putting that little thing and make it work, this is another little part of the test. So you would, for X now, let's look at it. What are the components here that I need to find? Let's highlight them with a different color. So there's one here. And there's one here already in blue. All right. So let's write them. So the first one is FAK, right? Which is assumed to be in tension, both of them. And then the next component is F, which I just found, FAC cos 30 equals to 0, right? So therefore, I can find FAK because that is equal to minus FAC cos 30. And now I found FAC before, which was minus bracket minus 480 cos 30. And now whatever that value work out to be, that's the force. And you continue using that right across it to find it. Let me see what that value is. Cost of 30, we know that as a standard cost, 0.866 times 480, I'm going to see. And I just chose some value. And so this would be 415.7 newtons. All right. So, and that is just demonstrating that, you know, so you take joint by joint. When you reach FAC is minus. So let me show you when you're taking the next joint. Let's say you're doing joint C. So joint C, let's draw joint C. I'm gonna take a little synopsis of this. And let me take joint C and just show you. I'm gonna copy. Let's copy this what I've done. So I'm gonna select it. I'm gonna copy this. I'm gonna show you now. And did I tell it to copy? I wanted to copy. Yeah, and I'm not gonna disturb it. Let's go over to another page. All right. Wow. That's what it does. Oh, I see. So I am gonna paste it. All right. I don't know why it keep on. I'm still learning this software. I'm not proficient at this software. I'm trying. Right. So what I want to do is just take a segment of it, but it's not giving me another opportunity to. Okay, let me just try and see if I can.
You're duplicating the page, sir, instead of creating a new page.
Where's the new page again? Let me see.
Right click on the page 2.
Oh, just click on it.
Yeah, you're gonna right click on the page 2.
On the page 2, it's not giving. It's not. I did that. This one I click the little box down the bottom here, but it duplicate the page. I asked it to give me a new page and it does. I don't know why it's not. Let me just click up here.
If you only to right click, they're not sure. They're not sure, sir.
Layers previous. Let me see. Document is not saved. I need another page. As I tell you. Okay. All right. Tell you what I'll do. I will just copy it. All right. It's all right. Let me just, because I wanted to, as I say, I'm not proficient at this. I just start using this one. So let me just show you the next joint on this page. So the next joint, oh, it's not accepting over here now. I'm trying to use another one. It's not working over here. All right.
I see a page with a plus sign at the top, sir.
Hold on.
At the top in the center, a page with a plus with a green plus sign beside it.
Hold on.
Next to the arrow.
Hold on. Give me a second. Let me just unstroke this. Yeah, where you see another page? You mean right here?
Next to the arrow, you have a page with a green plus sign. Keep going over to the right. Keep going right, sir.
Going to right here. Right up here.
No. Keep here? No, other way, sir. Keep going the other direction. Right next to the plus, not right next to, yeah, right. Keep going right. Yeah, that.
Yeah. Let me see.
Insert page.
Thank you. Thank you, sir. This is what I wanted. Yeah. Yeah. I just didn't get to go through the full thing of it. Yeah. So we got a new page. Thank you, sir. So this one we can delete that one. All right, cool. Nice. So all right. Let me just show you quickly. So we'd have done this joint before. All right. And we got some. So we're gonna just show you how to draw the next joint. That's all I want to show you. I want to show you full screen. It's full screen again here with a little more space. So here you need to consider joint C. So let's do joint C now. So joint C, so we're gonna consider joint C. All right. So you consider joint C. Now you would assume that AC, when we found AC, it was a compressive. So you need to draw it as a compressive force. So once you draw it into the joint, the sign becomes, you work with it as positive. So see there, this is this one right here. If you can see where my icon is, I know the icon is a little bit small. So once you go across here, all right, and the next one is CD. So let's draw in CD. We're gonna assume that CD is in tension though. Not getting a right, a straight line right there. So CD there. So CD there. And then now the next one is CK. We're gonna assume that that one is also in tension. See there? All right. It's a little bit skewed. Should have been 90 degrees. Hold on. Let me get that fixed. Right, let's go again with that. All right. So let's see. Come again. That looks more 90 degrees. Something like that. All right. So now we would have worked out these here. So we started out with them. We started out with them at 30 degrees. We had started it out as. I think we started this one at 30. All right. You could draw a straight line here. It means that this one is be at 30 also. All right. Right. And then therefore, if that one is at 30, possibly this one would be at 60. Right. See, it is 90. Remember, we started the original one at 30 here. So I'm saying a line here at 30. If this line is at 30, then this line here is going to be at 60. Right. And then from that, so you would have to map it now, draw your forces here. So you'll have one here, one coming down. So one will be positive, one negative for each element. And you do the same thing for the other force up top here. One positive and the other one gonna go up positive. All right. And the angle subtending there is 30. This angle is 60. All right. So how many? So you see you have several forces to work with. But this is demonstrating your understanding of the topic. So I needed to find as much force as possible. So you'll have one going up and you'll have one coming across. So one will be there for each force. And you're gonna use the same equilibrium equation. You would have known this was what was that one? That one was AC. Yeah, and you know AC already. So this was F, AC. This point is C, and this point is A. And up top was what? K, D. So up this was D. So you label them. This is F, C, D. And the last one would have been, this one would have been K. So this is F, C, K. Right? So all these components, you write the component for each one of them. This would be F, C, K sine 60. So one up here will be F, C, K cos 60. This one up here will be F, C, D cos 6 and a 60 cos 30. And this one up here will be F, C, D sine 30. Likewise, this one would be what now? If you have this one will be also 30 degree up here. Right? So this one will be F, AC sine 30. This one will be F, AC cos 30. So you'd have a number of forces. What you need to do, use the same equilibrium equation. I know I'm taking up a little of your time, but just explaining how to do that.
No,
So
man, sir, I was saying that I wasn't seeing anything, but it come up now. Yeah.
okay, so there you go. So all of those, you use your equilibrium equation. You don't need the moments one. You're not taking moments unless you're using method of section. And you look for each forces when you're doing the X, you look for all the X forces, right? And so forth. So if the X, let me highlight the X ones them in yellow. So the X ones, let's look for them. I'm gonna mark them now. The X1, can I see the, well, I tell you, one problem I'm having here is I can hardly find the X, the line. See, X, maybe yellow is not a good line to use. So I'm seeing the yellow, that is one. Another one, I'm overline it. See another one right there. See another X here. How much X we have? 3. All right. And let me highlight the Y with a red. Man, this thing is faint sometimes. So here's a red one. That's a Y. That's another Y. Come on, writer, don't do that now. Writer is messing up my page. All right. Let's see if I can find the next one. My writer is messing around sometimes. All right, here's another one. So we have 3 of them. So you have 3, you have 3 X and a 3Y components, and you need to put them in the equation and solve for them. You would have some of them already because remember you find FA, AC. So anywhere you put that in the expression, you have that value already. So it means you have something to work with. Because remember, we were up here and we found FAK, right? Which was, you see, you know this one and you know this. But in this one that we're doing now, C, you'd only know AC alone, right? You'd only know AC, you don't know CD, and you don't know CK. So that's all you do, and that is method of section, so you need to practice it, right? And you do it right across the frame, right? It's 5 of you, so everybody can decide to do that one, and you split up the work, and you just put the document together. So you design a bridge, find your forces, and just write up who you think made this type of bridge, which similar is it close to a warren, is it close to a truss, and you just write it up. And that's it, right? You can tell a little bit about it, just a little 1 page or a little half paragraph about the bridge and all of that. And that's it. I'm not gonna stress it because it's 10 marks, but demonstrate that you know to calculate the loads for me, please. If whatever force the truck have, you're gonna assume that it's at mid-span, which is at the center. So I want you to work with at the center. If you know the force at the center and it's mid-span, that means it's halfway between each support point, then you can calculate it. So automatically you know that if it's at the center and it is 480, for example, then half of it is going to be at AY. I already tell you that, and half one. But you can demonstrate it by your calculation by using your moments. You use your moments and get the value for me, demonstrating that you understand it and you're not just...
Sir, equilibrium or moment, sir?
Pardon me?
Sir, is it equilibrium or moments? Because you just mentioned moments.
I don't understand I don't understand your question. Please, sir, can you clarify?
Sir, you accidentally said the word moments a while ago, sir. I think you meant to say equilibrium.
Accidentally, I deliberately. It was deliberate, sir. Sorry, I just pick up my pointer. My pointer fell. Sorry, I had to reach for my pointer. Sorry about that. Yeah, let me tell you. I said moments because you take your moments. Remember, your moments equation also comes into play, you know. If you're finding reactions, then you can use your moment equation. Didn't you remember that? Yeah. Yeah, I'm freezing here. All right, get that thing off. All right, let me just see. Hold on. Right, my pointer stopped. No, it says drop. Do I still have it here? Can't find it. All right. Right. So yes, your moment equation. Once you find reactions, you must use your moment equation. So you could take moment at A and therefore you could find the force at B, right? And just demonstrate that you know to do it. And that whatever measurement you have between your deck point, you can actually show it. I tell you the value, but that is just telling the value. You can actually calculate it. It must demonstrate you know how to calculate reaction forces. Remember, you design a bridge, but you must do some academic work on it. You must demonstrate some calculation there. So, a minimum, your bridge might be having many members. Give each person at least two to three joints to do. Not everybody must do it. And I want to know who did what. So you write it down, the person who do joint one, you can just put it down and say, John did 2 joints. Those are the results, whatever. And you can check his work. You know, just take it for it. But you can write it down to show that John did something in the work. So John must demonstrate that he knows how to do method of joint or method of section. That's all I want from you. And the pressure is 10 marks. But demonstrate that you know to use method of joints and method of section. All right? And I'm still recording. I record because I want you to understand what is it that you need to do. All right, so I'm going to stop recording, and that's it, because a lot of persons will have to leave by now. All right, still have 23 persons. All right, so that's it. All right, so I'm out, sir. That's ladies and gentlemen, that's it for me today. And I do wish you have a wonderful time, and that the storm will not come. And next week we'll have bright and bright face-to-face class. All right, because I've missed quite a few of my students today.
Sir, I have a question.
Hang on a second. I want to stop my video. I'm looking for my where is my, I'm looking for my portal. Give me a second. Where's my, give me a second. Trying to get my recording portal. Where is it?
The question is regarding the bridge. So maybe it might be helpful if you let it stay in the recording.
Okay, go ahead.
Well, I wanted to find out if there's anything else that we should put in the document aside from the cost and the calculations for the bridge.
No, as I said, it's 10 marks. I'm not going to stress you guys. And I know you have a lot of work doing. And you have my test to prepare for and so forth, so forth. So I'm not going to stress you. Just do what you need to do. Write it up. It would have generated whatever the system generates. You can put it as part of the report. Right? So whatever the system generates, you can take it off and put it in the document as is. As a part of to show that one that you use the software and you didn't borrow the fork from somebody else. Okay, because the system should generate a report. You must put that whatever the system generates in terms of your bridge, put that as part of your report. You don't have to edit it. Put it as is.
Okay, sir. Thank you.
All right, sure. Good.